think it's time for us to begin. So thank you everyone for participating today in this SZ4D sponsored international webinar on subduction zone processes. And in particular, this webinar is sponsored by the Faulting and Earthquake Cycles Working Group of the SZ4D. I think almost everyone here has probably heard of SZ4D, but if you haven't, take a look at our website at SZ4D.org. Where we have some information about this US-based initiative to try to develop a new large-scale, long-term decadal program in research into the science underlying subduction zone hazards. The Faulting and Earthquake Cycles Working Group in particular is being guided by SZ4D Steering Committee members Emily Brodsky and Donna Shillington. Donna is currently in Alaska and about to get on the Langseth to do some marine geophysical research work up there. So we say good luck to the Langseth and hope that all goes well, even in this pandemic time, that they're getting some field work done. And you just heard from Emily if you were here a minute before the hour. I'm Harold Tobin, and I'm chairing the SZ4D Steering Committee. And I'm really excited today to have Dr. Shuichi Kodaira from JAMSTEC, the Marine Research Institute in Japan. JAMSTEC is actually, for those who don't know it, probably, I'd say almost certainly the world's largest oceanographic research center, and is responsible for a great deal of the amazing array of marine research that's happening around Japan and around the world. And a lot of that has been guided by Shuichi Kodaira. He's currently the Director General of the, let me get the name right, Institute for Marine Geodynamics. I think that's one of the newly organized institutes in JAMSTEC. I met Shuichi probably 20 years ago or so in the earliest days of thinking about the Nankai Trough project and some of the ways in which looking at subduction zones around the world would be advanced by really coordinated efforts internationally. Shuichi has been one of the absolute leaders in marine geophysics globally ever since, and certainly in Japan. I think he's the author of well over 200 publications and is really, published science that has had really seminal impact on our understanding of the structure and geometry, especially of subduction margins, including the Japan Trench and Nankai Trough that we'll hear about today, but also Izu Boning and many other places around the world. In particular about some of the really detailed geophysical structure of the plate interface zone, or the megathrust fault zone. So I think we have a great presentation today. Please do keep yourselves on mute and your cameras off so that we can have a smooth presentation and internet experience today. As questions come up to you, please type them into a chat box. I'll moderate those. I won't interrupt Shuichi unless there is an issue of a technical nature along the way, but we'll save the questions for the end, and then I will try to ask those questions in the order that they're put into the chat box. So without further ado, Shuichi, if you want to share your screen, we're looking forward to your presentation.
Yep. Okay, I'm going to share my screen, and can you see my screen?
Yes, looks good.
Yes. And I'm going to start my presentation. Okay, and then.
Yes.
Okay. I'm going to start my presentation, and first of all, I'd like to thank for inviting me this international webinar. I'm very happy to give talk about our research result and the future research plan. Okay, so for today's webinar, I'm going to talk about those 5 topics regarding a Japan Trench study since Tohoku earthquake occurred. And then I am going to recap the questions raised by the Tohoku earthquake study. And then in the very last part, I'm going to talk about the future research strategy to address those questions in Nankai Trough. Okay, I think you still remember very clearly about the Tohoku earthquake about 10 years ago. By this earthquake, we observed very much drastic geodynamic processes by geodetic and earthquake and tsunami observation network. And okay, so let's start with first my topic today, which is large sweep to the trench axis by this earthquake. So after the earthquake, many studies proposed core seismic sweep distribution using our data from geodetic, seismic, and tsunami observation. And of course, there is many models, and there is many difference. But the one important common character of the sweep, co-seismic sweep, is, as you know, very large sweep close to the trench axis. But those results obtained by a kind of remotely operated observed data. So it was unknown how far the large sweep had reached toward the trench axis. So in order to address this question, we JAMSTEC acquired bathymetry data soon after the earthquake as a part of rapid response crews. Our purpose of rapid response crews is to obtain the differential bathymetry in which we compare the bathymetry obtained before and after the earthquake. I think I have shown this figure more than thousands of times in my presentation, but the second figure from top shows the difference of bathymetry before and after the earthquake, and we have trench axis here. And from this figure, it is very much clear. We can see that the large core seismic sea flow displacement reaching at exactly trench axis, and also there is almost no core seismic sea flow displacement to seaward side of trench axis. And we are estimated co-seismic sea flow displacement about 50 meter in horizontal and 7 meter in vertical using this differential bathymetry data. And one thing I have to mention that uncertainty of differential bathymetry is quite large. Uncertainty are about 20 meter in horizontal and several meter in vertical. And then we also compared seismic structure before and after the earthquake along the differential bathymetry profile. So this is the before earthquake and this is after the earthquake. So by comparing the seismic image of the trench axis before and after the earthquake, we can observe the growth of fault and thrust structure in the trench axis due to the co-seismic sweep reaching at the trench axis, which also triggered local slumping at the landward side of the trench axis. So this is very much first geophysical or seismological evidence showing the trench breaching core seismic sweep fault by the megathrust earthquake. So those results may indicate need to revise a widely accepted conceptual model of subduction seismogenic zone in which the shallowest part of subduction zone is believed to be a aseismic or stable sliding region. But direct evidence I show in the previous slide is were only obtained along one single profile in the central part of the rupture zone. So we still had not known lateral variation of the sweep to the trench. So next topic is to answer that question. I'm going to show you the along trench variation of the strip to the trench. Okay, so to address the, to know the along trench variation of the strip to the trench, we processed additional differential bathymetry data. So along those three profiles. So this profile is the profile I showed before. In addition to this one, we processed those three profiles, and character of the differential bathymetry is quite the same as I showed before. Large co-seismic seafloor displacement extend exactly at trench axis and stop at the trench axis. And estimated horizontal displacement from those data is are between 34 to 69 meters. It's quite large. So it is very much clear that the co-seismic strip reaching at the trench axis can be observed at the central part of Japan Trench at around 38 degree north. But if you take a look at differential bathymetry profile about 50 kilometers south of the central part along this profile of Fukushima region, the differential bathymetry character is very much different from this one. We don't see any clear change of differential bathymetry at trench axis, and estimated horizontal displacement is almost zero along this profile. And also, oh, sorry. If you take a look at two more profile around 39 degree north, differential bathymetry does not show any drastic change of difference of bathymetry at trench axis in here and here, and estimated horizontal displacement just between 0 to 17 meter, which is less than uncertainty of differential bathymetry. And comparing the differential bathymetry pattern and co-seismic strip distribution obtained by, for example, geodetic and seismic data, they are very much consistent each other. We observed very large strip only in around the 30.38 degree north, but almost zero or very little co-seismic seafloor displacement at 50 kilometer north and 50 kilometer south. Okay, and another important evidence showing variation of the strip to trench is geological evidence. The geologists from JAMSTEC and Geological Survey Japan, Ikehara-san and Kanamatsu-san and others, they they collected piston core sample and the strong cooperation with European group. And this figure demonstrates that they observed 3 sets of earthquake turbulate from core sample, which correspond to the Tohoku earthquake and 1454 Kyotoku earthquake and 869 Jogan earthquake. And the more important result they found is those 3 sets of the earthquake turbulate only observed in the central part of Japan Trench axis around 38 degree north. This result also shows strong lateral variation. And also another important geophysical evidence showing large variation, long range variation are obtained by GPS acoustic monitoring. Tomita et al. 2017, they processed 4 years GPS acoustic data since 2012, and they observed strong along trench variation. For example, landward large landward displacement in the large slip region, co-seismic slip region, and also trenchward displacement in the southern part, and also slight trenchward displacement in the north, seaward displacement in the south. And those variations are interpreted as viscoelastic relaxation in the large slip region in the central part of Japan Trench, and also rapid after slip in the south, and also combination of the after slip in deeper part and fault locking in shallow part at the north of the main rupture zone. So those line of geophysical, geological, and geodetic evidence shows that large co-seismic slip leading to trench only occurred in the central part, only occurred in the compact region of central part of Japan Trench. So this shows that very strong lateral variation of the slip to the trench along Japan Trench. Okay, then next I'm going to talk about the factor controlling variation of the slip to the trench. So one of the important purpose of the famous IODP JForest project is to answer this question. What is the factor to control the large slip to the trench axis? And JForest group, they successfully observed that 5 meters thick pelagic clay along the plate boundary fault, and also the laboratory experiment using core sample from JForest site, and also temperature measurement at downhole sensor of the JForest site shows the very, very low frictional coefficient. So from those results, the JForest group suggests that the pelagic clay may be regionally important control on our shallow or megathrust slip or tsunamigenic slip. But things are more complicated. Recent biomarker study shows that multiple faults have hosted more than 10-meter seismic slip around the pelagic layer, and several faults are observed within the mudstone above the pelagic clay layer. So this result indicates that histological contrast and frictional property do not necessarily determine the large slip in the shallow part. So, but those multiple faults is around the pelagic clay layer. So I personally think physical contrast of large contrast of physical property between chert and clay layer is probably one of the important factors to control the shallow co-seismic slip. So input sediment may be one of the possible factors to control the large slip to the trench, but we need more study. But the role of the input sediment remains controversial. So to examine the structure character of the input sediment to subduction zone, the active source seismic group in JAMSTEC have been studying the detailed structure and distribution of the input sediment. And Nakamura and others 2013, he showed the seismic section as a kind of common structure of the input sediment, which shows the seismically well stratified layer in the upper part of sediment, and also seismically scattered layer at the bottom of sedimentary package of input sediment. And comparing the seismic section and result from DSTP site 436, which is in here, the Nakamura and others, they conclude that well-stratified layer and the seismically scattered layer correspond to the hemipelagic mudstone and crater chert layer respectively. And more importantly, DSTP result shows that the thin pelagic clay is kind of sandwiched between mudstone, well-stratified mudstone layer and seismically scattered chert layers. So those structure is kind of common seismic structure of the incoming plate in the most of the Pacific plate entering to Japan Trench. Recently, Fujie and also 2020, he showed that similar seismic character entering to the main rupture zone. But in some place north of the main rupture zone, he also observed a very different sedimentary structure, which shows the very thin sedimentary layer and lateral continuation of hemipelagic mudstone, pelagic clay, and crater chert layer is broken because of this very different seismic structure character. And also, in order to know the distribution of this input sediment to the Japan Trench, Fujie and others, they compiled all available seismic data to show the thickness variation of the input sediment, and they found that there is some spot showing very thin sediment in here and here. And in this diagram, they plot the area where we observed well-stratified layer and the scattered layer, which consist of the hemipelagic mud and the Cretaceous chert as red lines. So in the thin sediment layer, they found the break of lateral continuation of the flat sedimentary layer in here and here. And actually, this region is correspond to the area previous study observed young volcanic activity, so-called petit spot, where they observed lots of seal and dike intrusion into the sediment. So from those observations, the Fujie and others conclude that post-spreading volcanic activity on the oceanic plate before subduction is one of the factors that control the size and distribution of the input seismic slip after subduction. I probably forgot to mention that the main rupture zone is here, and he observed a patch of the disturbance of sediment region in here. So he concludes that this structure variation is one of the factors to control the northernward continuation of large slip. And also, if you take a look at southern part, there is many seamount is subducting right now, and Moore et al. Propose that the occurrence of seamount also break the continuity of the pelagic clay layer that controls the lateral propagation of large slip to the trench. So also, that's why this is, of course, one of the interpretation. We have very much disturbance of input sediment in northern and the southern edge of the large rupture zone. But fault slip behavior must be complexly controlled by various factors, not only input sediment. So further research is necessary to elucidate a factor to host the large slip to the trench axis. Okay, so next topic is a source of the tsunami generation. at the nose of the main rupture zone. As I mentioned before, the core seismic slip distribution obtained by geodetic and seismic, and also structure variation, and also result of differential bathymetry are consistent each other very much. All those results indicate no or very little core seismic slip reaching the trench axis at around 39° north, around here. But there is one problem to take into account the tsunami data. The core seismic slip distribution obtained from tsunami data required additional tsunami cells at around 39° north, around here. So we still don't know what's happening around here. What is the source of the tsunami, large tsunami from this region? So one of the kind of working hypothesis or working idea is inelastic deformation of the frontal prism close to the trench. For example, Tanioka and Seno 201, they proposed inelastic deformation of the frontal prism due to the seaward movement, landward block by the core seismic slip at the deeper part. Actually, our seismic data shows the frontal, low velocity frontal prism structure extending from central part to the northern part of Japan Trench. And another possibility is maybe a submarine landslide. Recently, Nakamura and others, 2020, he compiled high-resolution seismic data acquired along this white box, and the seafloor geometry and subsea floor structure showed some evidence of the submarine landslide to the trench axis. So this may be cause of some tsunami, but the problem is we don't know the timing of the submarine landslide in this region, because we only have the seismic data acquired after the earthquake. And also, more important things we have to explain is the displacement in this region should be less than uncertainty of differential bathymetry, which is about 20 meters in horizontal. So we have some working hypothesis, but we still don't know exact reason of additional tsunami cells at around 39° north. Okay, so next is interaction with fault activity in the outer trench slope. So there is a very big change of seismicity before and after the Tohoku earthquake. For example, this diagram shows the earthquake mechanism of the earthquake before earthquake, which shows the most of event were interplate earthquake with thrust type fault mechanism. But this seismicity changed very much by the Tohoku earthquake. After the main shock, thrust mechanism earthquake did not occur within the main rupture zone, but thrust event occurred in the surrounding region. And also, the normal fault event were activated in the overriding plate and also the outer trench slope. So we have been studying about activity, seismic activity in the outer slope region after the Tohoku earthquake because the past observation shows that the large normal fault, outer large normal fault occurred as a pair of the earthquake with the large shallow megathrust earthquake. For example, 1896 Sanriku earthquake and also 1933 Sanriku earthquake is typical pair of the earthquake of shallow megathrust and a large outer large normal fault. And similar doublet of the earthquake, megathrust and normal fault in the outer trench are observed in Aleutian, Kuril, and Tonga Trench. But if you take a look at 2011 Tohoku earthquake, we got a magnitude 9 megathrust earthquake, but in outer trench slope region, we only got magnitude 7.6 normal fault soon after the earthquake. We didn't get any magnitude 8 class normal fault earthquake in the outer slope region yet. So in Japan Trench, large outer trench slope normal fault earthquake is very much concerned after the Tohoku earthquake, but we still didn't know the distribution, geometry, and activity of the fault to host outer trench slope earthquake. So in order to obtain information about outer trench normal fault earthquake, we have been acquiring active and passive seismic data and also bathymetry data in the outer trench region after the Tohoku Oki earthquake along those profiles. Okay, so first I'm going to show you the bathymetry and also seismicity within this white box seaward side of large rupture zone. So this map shows the bathymetry map in which we enhanced slope changed of the bathymetry, and also blue dot indicate aftershock activity observed by the OBS network deployed after the earthquake. So from this figure, we observed very strong horst and graben structure, which mostly parallel to the trench axis, but we observed some oblique horst graben structure. And more importantly, we observed several lineation of the seismicity. And most of them are observed within the graben region, like this, and here, and here. So those maps clearly shows that multiple normal fault activated by the shallow megathrust earthquake. And then let's take a look at the seismic section in the outer trench slope region. So as we expect, we observed very strong horst graben structure, and taking a look at the offset of the basement, the very high deep angle normal fault is necessary. Like this. So deep angle is between 70 or 75 degrees, which is a quite high deep angle of normal fault. And also, if you take a deeper part, unfortunately, the seismic image of the normal fault cannot be observed from seismic section. But if you continue to high angle normal fault to deeper part, those fault can explain very well break of lateral continuation of Moho reflection. But the global earthquake data shows that the dip of fault is about 45 degrees. But if we accept 45 degree dip of the fault should be like this, and this 45 degree dip fault cross the lateral continuation of Moho reflection. So that means the 45 degree dip fault is unlikely to explain the seismic image. And then we plot the aftershock distribution on the seismic section. And of course, the seismic, hypocenter is scattered a little bit due to the uncertainty, but very high deep angle normal fault can explain the location of the cluster of the aftershocks, something like this, and also like this and like this. And if you take a look at another section, we observe the cluster of the aftershock along the deeper continuation of high deep angle of the normal fault. And even though we don't observe any seismicity, high deep angle of normal fault can explain very well break of lateral continuation of a Moho reflection. Okay, so from those data, we map the distribution of the potential source fault of the outer trench normal earthquake on this map. And important point is by the shallow megathrust earthquake, several normal fault along Horst graben are activated. Multiple faults are activated. And the next things we have to do is to prepare outerlies earthquake tsunami, and we need to do tsunami simulation and also update the tsunami early warning system using the realistic fault parameter we obtained from geophysical study, and also to examine the stress state of the outer lies fault after the shallow megathrust earthquake. We have to estimate the stress preservation for the normal fault using a realistic fault parameter we obtained. Okay, so let's summarize today's my talk about what we have learned from Tohoku Oki earthquake. So the first point is our tsunamigenic large cross-seismic sweep can reach at the trench axis. And second is the large sweep is observed in the compact region of central Japan trench. And there is no clear evidence showing the large sweep to the trench axis in the northern and the southern part of the main rupture zone. And the spatial correlation between the large sweep zone and distribution of the input sediment to the trench is observed. And also, we observed activation of normal fault earthquake in the overriding plate, and also outerlies trench slope by the shallow megathrust event. And the outer trench slope earthquake will activate along multiple fault with very high deep angle. And also, oh yes, and I didn't mention at all at today's my presentation, but some study shows that possible transient slow slip as a precursor of the megathrust earthquake, like Ito and Kato et al. Okay, but we still we still have many questions need to answer. For example, first one is, what is the factor to control the spatial and temporal variation of sweep behavior of shallow megathrust sweep? The input sediment is probably factor, but need to more study. And second is, what is the tsunami source where large fault sweep may not occur, like 39-degree nose in Japan trench, and whether or not large outer trench slope earthquakes ready to occur, and how large tsunami we should prepare from a potential outer trench slope event. And also, does precursory slow slip always occurred before large megathrust earthquake, and what is the mechanism of the precursory slip? And as a general question of subduction earthquake, how have plate coupling changed before, during, and after a large megathrust earthquake? Okay, and to answer those questions, I think we need to capture slip behavior before, during, and after a megathrust earthquake. And for doing this, the Nankai Trough is one of the best test site because we know that chance of the great earthquake in Nankai Trough is very high right now. And also, more importantly, especially in the Nankai Trough, capturing processes of before, during, and after megathrust event is a very much fundamental scientific approach to mitigate earthquake tsunami hazard. So let's take a look at earthquake in Nankai Trough. I think many of you know already about the earthquake history of Nankai Trough, but we can trace the history of our earthquake more than 4,000 years ago using historical literature and paleoseismological data. But if you take a look at closely, the earthquake interval are not uniform. Interval are fluctuated between 90 to 260 years. And also rupture zone is very complicated. In each cycle, either a pair of earthquake occurred or a single earthquake ruptured in the entire region. So those diversity make it very difficult to estimate the future earthquake based on our historical data. So what we have to do, what we need to do is to understand the slip behavior, its temporal evolution. And to do that, we have to know the slip and coupling at present, and also we have to estimate temporal variation of the coupling to the future. And to do that, what we are thinking right now is we have to develop real-time continuous seaflow geodetic network, and also we have to construct a realistic large-scale 3D structure model, and we need to develop the technique to estimate the temporal evolution of coupling. So I'm going to briefly current state of the monitoring. The Japan Coast Guard, they successfully deployed seaflow acoustic network and successfully mapped the coupling in here, but temporal resolution is not as high as to detect short-time slow slip event, so real-time continuous geodetic data are necessary. So one of the very nice example to observe the continuous seaflow geodetic data was done by the Nantrosis group. They deployed a borehole pressure sensor, and Alaki, Seifor et al., they successfully observed transient variation or pore pressure within the 2 weeks, and they estimated 1 or 2 centimeter slow slip along the plate boundary. And more importantly, they found that those slow slip events occurred regularly along the plate boundary, and 30 to 50% of strain were released due to because of this slow slip. And another approach the JAMSTEC scientists are doing right now is to utilize DONET, the tsunami sensor, as a geodetic sensor. As you know, the tsunami pressure gauge has instrument drift. So we needed to calibrate the pressure sensor. So we developed a mobile pressure calibrator to carry out in situ calibration. And the JAMSTEC group, Alaki and others, they successfully calibrate, precisely calibrate the DONET, the tsunami sensor, using mobile pressure calibrator, and they calibrated pressure sensor of the DONET station with resolution of less than 1 hectopascal, and at one station they estimated 2.2 hectopascal per 6 months as a drift rate. Okay, so in the future strategy, we are going to develop the seafloor geodetic network under the very strong collaboration with NIED, who are now operating a DoNet system. And we are going to calibrate all DoNet pressure sensor using mobile pressure calibrator. And also we are going to install borehole observatory using a seafloor drilling machine or a Chikyu drilling vessel. And also we plan to deploy a geodetic sensor to the scientific node of new earthquake tsunami network, so-called NNet, which plan to deploy west of the DoNet area. And okay, and yes, let's take a look at the seismogenic zone model and the modeling method in Nankai Trough. So as I mentioned, the Coast Guard, they obtained geodetic data, and recently many researchers estimated plate coupling using the same data set. For example, those three figure shows plate coupling using same data, but using different model. So due to the difference model, the plate coupling pattern is quite different. For example, if you take a look at slip zone of Toho Nankai earthquake, a strong coupling in here, but a weak coupling in here. So this is because of difference of model. So what we need is we have to establish a realistic community model of seismogenic zone to utilize the seafloor geodetic data. So to construct 3D model, we already compiled all available structure data, and we constructed this overall 3D subduction model. But if you take a look at a recent study, some study proposed at the split of the plate in here, and also some study presents the kind of patchy-like distribution of slow slip, indicating a patchy-like distribution perturbation of plate coupling. So we need to know the more shorter wavelengths of structure variation of the plate boundary. So, so to address this issue, we are now doing a large-scale 3D or dense 3D 2D seismic survey to cover the entire DoNet and NNet region. And in the last 2 or 3 years, we acquired this kind of dense 2D seismic profile. And actually, our ship is just around here to acquire more data. And so far, we obtained this kind of map showing the very much shorter wavelengths of perturbation of plate geometry, which indicate undulation of plate interface around subducted seamount, where we observed a cluster of the low frequency band. Okay, and also we need to develop the modeling technique to use the realistic model, 3D model we are going to obtain. Okay, so this is last slide. To answer the question we got in Japan Trench, we need to capture the before, during, and after the earthquake. And And to do that, I think Nankai Trough is the best place, and we plan to develop the network and construct a 3D model and develop the new technique to using a 3D model and also real-time continuous seafloor geodetic data. Okay, so this is everything I want to present today. Thank you very much.
Thank you so much, Shuichi. And if everyone could clap and be heard, then I'm sure you would hear a lot of applause right now. That was a fascinating and really full of information presentation. Please, anyone who has questions, go ahead and type them into the chat window now. They are beginning to accumulate, so I'll just launch right in so we have the most time we can. First one listed there, Roland Bergman asks, do the seismic reflection data in the outer rise reveal the likely source faults of the magnitude 8 1896 Meiji Sanriku rupture? So does
Yes.
reflection data show you the rupture fault for that 1896?
Actually, as I mentioned, our seismic section does not see any fault image within the crust. It's very hard to see the fault image as reflection. But I think we based on the bathymetry data, we can map the very long potential fault, something like that. And this area is probably correspond to the proposed area of 1933 normal fault earthquake. So my answer is we cannot see the fault itself, but we can trace those faults based on the bathymetry data, plus some weak seismicity. Is that?
Yeah, thank you very much. Let's see. Onur asks us, thank you very much. Asks you, are the earthquake locations improved by, for example, double difference method? What are the uncertainties, kilometers or meters?
Yes, of course, the uncertainty should be improved by the different double difference method. We should do that. So right now, the uncertainty or error of the hypocenter is something like that. I got this figure, my colleague Obana et al., and he brought uncertainty of something like this. This is slightly outside of the outer region, but uncertainty is the same. So this is current uncertainty, but if we apply double difference, it should be improved very much. We should do that.
Great, thank you. Andy Newman asks, could you discuss the largest challenge to getting better lateral resolution in the repeat bathymetry, since 20 meters is a large uncertainty?
Sorry, say again?
What are the challenges to improving the resolution of repeat bathymetry?
Improve the resolution of repeat bathymetry. Well, yes. There is many factors to make uncertainty. For example, location of ship, and also we don't know the structure of the seawater, temperature, salinity, that very much affect to the seafloor data. So if there is any way to estimate the water column information, I think we could improve the resolution of differential bathymetry more. Yeah, that is what I'm thinking right now, but there is many other things we can do. I'm gonna think about that.
Great, thank you very much. Yeah, lots more questions, so I'll just keep going while we still have a few minutes. Excuse me, Jeff McGuire asks, can you tell us more about the plans for using the seafloor rock drill to install continuous geodetic sensors? Seafloor drilling, you know, I forgot the acronym, but the seafloor drill to install geodetic sensors, and has that approach been successful so far?
We just started, and last year the people from Araki's group in JAMSTEC, they use the seafloor drilling machine, and they made some shallow hole, 5 to 10 meter, if my memory is correct, and they deployed tilt meter, but it's still testing phase. So we have to carefully evaluate the quality of data and also coupling of sensor and so on. We just started. And this year we're gonna deploy more station. You are in mute. Harold, you are in mute.
Thank you very much.
Yes.
I wanted to just address one question. Will the presentation be available? And yes, we are recording this webinar and that will be on the SZ4D website. I'm not sure about the PowerPoint slides, but the webinar recording will be available. Ling Chen asks, I wonder if there is any lateral variation in the structure and properties of the bottom of the overlying plate that may affect the slip behavior.
Bottom of overlying plate.
Yeah, so you brought up the incoming plate sediments, for example.
Yeah, right.
Other things.
Yes, that should be variation on the bottom of the overlying plate, but it's not easy to image of the bottom of the overlying plate. The bottom of overlying plate is kind of just above the top of subducting plate. So we can image the top of subducting plate down to 25 kilometer. And yes, seismic reflection shows the top of the oceanic plate down to that depth. And we see some geometry. And we have several 2D profile, but that the density of 2D profile is not enough to discuss of the detail or precise variation, 3D variation. We need more data. We have the potential to image that interface variation, but we need more data.
Yes, thank you. Okay, Charlotte Rowe asks, is someone using correlation repicking to improve the illumination of small scale structures?
Sorry, I don't understand.
Correlation repicking.
Correlation of what? What did you say?
Yeah.
Say again.
Correlation repicking. So I assume that refers to picking of the events and using some sort of correlation techniques.
Event means earthquake. So to the question is, in order to get more accurate picking.
Yeah, she clarified seismic phase repicking using waveform cross correlation.
Yes, of course. So we should do that. We just pick up the travel time, but waveform correlation should improve the picking of the earthquake very much. Yeah. I agree. Yes.
There are many questions rolling in. We won't have time for all of them, but I'll ask one or two more while we still have a few minutes. Victor Cruz Atienza, to your knowledge, is there any geodetic data inversion technique capable of imaging slow slip events and coupling simultaneously?
Geodetic slow slip and coupling simultaneously. Yes. To do that, we need, as I mentioned, we need kind of continuous data. Now we have the plate coupling. I think you can see my slide in here. The plate coupling, this is those data obtained by seafloor geodetic data, which observed, for example, every 6 months and so on. So then we can observe the plate coupling. But to estimate the slow slip, this data cannot resolve the slow slip. So before we develop the method, or in addition to develop the method, we need the data to monitor the continuously of the plate coupling. Then if we can apply plate coupling estimation, for example, every day or something like that, we can estimate, we can make a snapshot of plate coupling, which may resolve the slow slip event. Yes.
Yes. Okay, so I want to remind everyone that we have kept Shuichi up until 2 o'clock in the morning, his local time. And there are many more questions and really good ones in the chat that we just don't have time to get to. So I want to give one or two reminders of upcoming SZ4D talks, and then we will thank Shuichi one more time for this fantastic presentation. But upcoming, we have on September 11th, Martin Demore and Mauricio Mora, who will be speaking on topics of volcano work in Costa Rica, I believe. And after that, the next one in the earthquake speaker series will be Victor Cruz Atienza, who's on today. So we look forward to both of those talks and many more to come as we will continue this this SZ4D International Seminar Series, learning about what's going on in research around the world on these subduction zone processes. So on behalf of everyone who's been watching, and I noticed that we had at least 160 people online during this presentation, I want to thank you one more time, Shuichi, for a fantastic presentation, really informative. The thank yous are rolling into the chat, which we will send you afterwards. And thanks everybody for joining in.
Thank you very much.
All right. Until the next time, folks, please enjoy your weekend. Shuichi, really enjoy your Saturday and Sunday.
Thanks very much. Yes.
Thank you so much for being here.
Yeah, thank you very much. It's very good for me too.
All right.